All right, in this next section, 10.3, we are going to look at convergence of series with positive terms, and really this section is going to present to us various tests that we can use. And how we can figure out whether or not these series converge. In this section, we are less concerned with what the series converges to and more with just does it converge at all. We will come to a point later on in a later section where we can estimate things, but for now we're really just interested in does it converge or not. Okay, so we have this integral test. So the integral test is related because we know from Calc 1 that really a definite integral is an infinite series. So there should be some sort of association or at least a correspondence between the convergence of infinite series and the convergence of a definite integral, because really they are very much related. So the basic idea is the following. If we think of let's just go ahead and take a look at a particular series here. Let's say, let's go ahead and take a look at example 1. We'll illustrate this integral test via example 1. So in example 1, we have 1 over the square root of n from n equals 1 to infinity. So what I can do here is sort of pull out the series term, 1 over the square root of n, and I can sort of make this a continuous thing. So this right now, this is a discrete function. We can examine its continuous analog, which is a function, let's call it f of x, and that is 1 over the square root of x, or we can write this as 1 over x to the 1/2 power. So now let's graph this. So all functions 1 over x raised to some power, they all have this basic shape. They all have that basic shape. So here is our y equals 1 over x to the 1/2 power. So if we have this series from 1 to infinity, let's think about what these terms look like. These terms look like 1 over the square root of 1 plus 1 over root 2 plus 1 over root 3, 1 over root 4, so on and so forth. So if we have this 1 over the square root function, then if this is x equals 1, then this value right here, that would be our point. And I really would like to blow this up a little bit, just make it a little bit bigger. I should have drawn this bigger. It's going to be a little bit too big now, but whatever. This works well. So if that's 1, then this would be 1 over the square root of 1. This value here, if this is 2, then over here we would have 1 over the square root of 2. If this is 3, 1 over the square root of 3. So the separation between each of these, let's say we just make this a little dotted line. If we think of this separation here horizontally, this change in x is 1. And that's true here as well because we've got 3. So yet again, we've got a distance of 1. So if we create a rectangle here, then this rectangle here has a width of delta x equals 1 for all of them. And the height of this rectangle is going to just be the function with our left endpoint plugged in. So this first rectangle here is 1 by 1 over the square root of 1. So the area of this rectangle is exactly this first term. Similarly, the second rectangle also has a width of delta x, which is 1, and it has a height of 1 over the square root of 2, or f of 2. So hopefully a picture is forming here that this particular Riemann sum with delta x equals 1, this is exactly representative of this sum here. We're adding up all these areas. So essentially, this series is related to the integral from 1 to infinity of 1 over x to the 1/2 dx. So what we have to keep in mind here is if we look at this function, because this function is a decreasing function, we know that these rectangles of the Riemann sum, they are all overshooting by a little bit. So this Riemann sum here, it is related to this, but not only is it related to it, it is specifically an overestimate for the integral. Because each of these rectangles, there's a little bit that hangs over, and that is additional area than the integral. Because of course the integral would give us, this exact area under the curve. So this is going to be an overestimate. And because of that, we can essentially use what we already know about improper integrals and the comparison theorem. We already know that this integral is a p integral. So it's a p equals 1/2 integral, which is less than 1. So this integral here diverges. So if this inequality is true, and we found the lower bound diverges to infinity, then by comparison, and again, for comparison theorem, we do need these things to be non-negative, and clearly this is going to not be negative, so we'll just go ahead and sneak that little last part of the inequality in. So then by comparison, this integral here from n equals 1 to infinity, 1 over that, diverges to infinity also. So the entire idea for the integral test is that an infinite sum can be related to the Riemann sum, which defines the definite integral. So if our integral converges, then our series converges. If our integral diverges, then our series diverges. So they behave the same way. They behave the same way. Okay, we can take a look at example 2 to determine whether the series converges or diverges. So again, we can sort of relate this the integral from 2 to infinity, 1 over x natural log of x. So we can compute this using a substitution. let u equal natural log of x, so then du is 1 over x dx. U of 2 is the natural log of 2, and then if we take the limit as x goes to infinity of u of x, which is just the limit of natural log of x as x goes to infinity, we will get infinity. So this integral here becomes from natural log of 2 to infinity. We will have 1 over u du, which is the absolute value of u between natural log of 2 and infinity. Well, we can use another limit here, so let's go ahead and do that. The limit, as let's say r goes to infinity, make this upper bound a capital R. So then this is the limit as r goes to infinity of the natural log of absolute r minus the natural log of the absolute value of the natural log of 2, which is infinity. Because the limit of natural log of something as that something goes to infinity is infinity. Natural log is a strictly increasing function. So we get infinity here. So what we what we will absolutely have to do is write out a formal conclusion. Example 1, I didn't really do that. I was more or less trying to emphasize and give some intuition behind this integral test and why it works. So for example 2, we can relate it to this integral. But there are hypotheses that we have to satisfy before we can actually make this conclusion. So looking back up here at the integral test, we have to make sure that our function is a positive function. It has to be decreasing, and it needs to be continuous for x greater than or equal to 1. So this function here, 1 over x ln x, both x and natural log of x are increasing functions. So 1 divided by an increasing function, that means the entire fraction is decreasing. So it is decreasing. So if our function f of x is defined to be 1 over x natural log of x, then f is decreasing. And generally speaking, you don't have to go crazy justifying this unless really it's kind of hard to tell by looking at it. Here, because our numerator is constant and our denominator is increasing, it's very clear that the function is decreasing. So you can just state it because it should be obvious at a Calc 2 stage that this would be decreasing. So f is decreasing, check. F is positive, right? Because, x is definitely positive when x is greater than or equal to 2, and natural log of x is greater than 0 when x is greater than 1, so this being a 2 checks out, so that's good. Okay, so that's good. It is definitely positive. Okay, so positive, decreasing, is it continuous? Yes, f is continuous. And unless there's something really weird going on, you shouldn't have to go crazy justifying this. So f is continuous. There are discontinuities at x equals 1 and x equals 0, but those are not over our domain of integration, so there's no issues here. So if our function if our function is defined to be this, then these three things easily follow, in which case this means the conclusions of the integral test will hold and be valid. So since we found that this integral diverges to infinity, we can say by the integral test, so must the series from n equals 2 to infinity 1 over n natural log of n. So it's extremely important that you actually go through and verify these. You don't have to go crazy doing a lot of work unless it's not obvious to you if it's decreasing, positive, or continuous. But you do need to state them because it is important that we are checking these hypotheses.